Hi everyone, my name is Matteo and welcome to my flash talk of this Neuromatch conference. In this work, we try to understand the computational role of spikes for predictive processes, and I will try to show you here that spikes can be a good representation to learn predictive relationships between events, and that neurons can solve complex credit assignment problems in time by adjusting their own synapses for those predictions. This concept we call predictive plasticity. And we show that several STDP mechanisms can naturally emerge from our predictive model. We do so because we are interested in predictive processes happening in the brain, and the prediction of the future is, of course, a loosely defined concept, but here we cast it with 2 bullet points. For a system to predict the future, it is likely critical to, first of all, give credit to those inputs that are informative about the upcoming events, and to discard the ones that are predicted. And on top of that, a system would like to anticipate or signal events ahead of time. Here, we are studying those predictive processes at the single neuron level specifically, and we ask what is the role of spike timings for the prediction of the future and in the learning rules that the neurons could use in order to learn those predictive relationships. How we do so? We use a computational model of the dynamics of the memory potential of a cell, and on top of that, we define an optimization problem in time. We show how can this be biologically implemented at the level of single neurons, and how this can be made online, which means that the synaptic plasticity, the update of the parameters, happens simultaneously with the dynamics of the input itself, of the system, sorry. So let's imagine that we have time, and we have discrete time steps. The model works this way. Let's imagine we are at time step t-1. The memory potential of the cell is a linear system of the past events, of the past inputs. So what it does at this time step, it takes the memory given by the linear filter of what happened before, and it includes the new input arriving at time step t-1, which has been encoded through the synaptic weights. This would be the variable that the neuron will use in order to compute the prediction in the future. Indeed, at the future time step, the neuron uses the memory potential of the previous time step together with the synaptic weights in order to compute a prediction, which is represented here, of the input that it is receiving now, which is represented here. The mismatch between the prediction and the actual input is a prediction error, which is the main drive of plasticity. At the same time step, the neuron indeed updates its synaptic weights, and we will use the new synaptic weight vector in order to make novel predictions in the future. And this will happen constantly, over and over in time. I will show you now a bunch of results. First of all, in a simple case in which we have 2 inputs, that there are 2 spikes coming from 2 different presynaptic inputs with a 4 milliseconds delay between the 2, when we train the model on this very, very simple scenario, we see that the neuron learns to fire ahead in time and to fire between the first input and the second input by maximally increasing the synaptic weight of the first input and suppressing the second. This because the first input, because it comes always before the second, it has a predictive power on the occurrence of the second spike. Here we show the dynamics of the weights and of the output spike time across epochs. And here in the parameter space given by W1 and W2, you can see with this flow field that independently from where you start in the parameter space, you will converge to the anticipatory solution because this solution is a fixed point of dynamics. Of course, in the real brain, the sequences are way more complicated. So what we did here, we simulated a more complex biologically plausible sequence by considering 100 neurons that they create a sequence that spans 200 milliseconds. We took this deterministic sequence and we plug it into the higher dimensional input where there are other 100 inputs that they don't belong to the sequence. They just fire randomly. We added random background firing and jitter in the spec time for the neurons that they do belong to the sequence. And here I'm showing different epochs of training. As you can see, the firing rate of the presynaptic population is always constant. So there are no cues in the changes of firing rate to know when the sequence is starting. As you can see here, this is the output spike time across epochs. And after a starting point, when learning goes on and on, the neuron learns to fire earlier and earlier in the sequence, and eventually it converges to fire only for the first input of the sequence itself. This is driven by synaptic plasticity. Here, this is the dynamics of the weights of the inputs that they don't belong to the sequence, and those ones of the ones that they do belong to the sequence. As you can see, as learning happens, the neuron amplifies earlier and earlier inputs across the sequence, and at the end of training, only the first input is the one that gets maximally amplified. Because learning follows the graded descent of an optimization problem, we see that the loss decreases across epochs, and also the amount of depolarization decreases across epochs. Here, I'm going to show you how STDP can emerge from this predictive model. Let's recall the parameter space we saw before of the two parameters. As I told you, the anticipatory solution is a fixed point of dynamics, but the way the synaptic weights will change in order to converge there, it will depend from where you start. Let's imagine that we start here, where we have one output spikes given after the second input. This scheme is exactly equivalent to the pre-post pairing in STDP experiments. And if we look at the dynamics of only of the pre-synaptic inputs that comes before the spike, we will see an increase. Whereas if we are here and we look only at the post-synaptic input, we will see a decrease. When we try to quantify this by changing the delta t between inputs, we basically obtain, as an emergent phenomena, an STDP learning window. And we are also able to fit several nonlinear STDP mechanisms quantitatively with our model. So I hope you enjoyed, and please just contact me for whatever question. And here you can find the QR code for the bioarchive.